let's say I have a yellow ball moving round in a circle. Now, I'm interested to find out more about the force that causes it to go round in this circle. So let's see. So suppose that I have at first the ball is here and it has this velocity in this direction with a speed of magnitude, with a speed v. Okay, and let's now to find out about the force, I'm going to use this idea, what we know, that force, according to Newton's second law, is related to acceleration. Force is mass times acceleration, and we also know that acceleration is equal to the change in velocity, the change in velocity divided by the time taken. So in other words, the force that causes the change in the force is in the same direction as the change in velocity. So this is what I'm going to try and find out. I'm going to try and find out the direction of this change in velocity. Now this is a bit tricky because the velocity itself changes direction. So let's see how we can do this. So suppose that the velocity, suppose that it's moving here with a speed of 3 meters per second. Okay, and that after a time, now I'm going to think about an angular displacement. So let's say this direction is a reference direction, and after a time, the ball moves to a new position with this angle here that is 60 degrees. So in radian, this angle would be pi over 3 of a radian. And then the ball would then be here at this time. And so when it's here, the direction of the velocity would be along here. So then the new direction, but the magnitude is still v. It's the same magnitude. Okay, but the direction would be different. Now, what would be the new direction? How would be the angle compared with the original? Right. If we look at the easiest way to think about it is to look at this reference direction for the angle. If you look at this reference line joining the center of the circle to the ball, and you look at the direction of the velocity, clearly they are at right angles. So when the ball has moved to another position, this line joining the center to the ball is still at 90 degrees to the new direction of the velocity. So that angle doesn't change. And what this means is that if the ball is the angle of the ball is changed by pi over 3, 60 degrees, so the angle of the velocity must also change by the same angle. Next, I want to think about finding this change in velocity. Now, the way to find the change in velocity is always to take the final velocity minus the initial velocity. So that's the final velocity, that's the v, that's the initial. And since both are vectors, I can just find the difference by subtracting the two numbers. Okay, because vectors has the direction information, and the proper way to subtract them is to do it by drawing, say, a triangle. I'm going to take each vector and I'm going to move it, keeping the directions the same. I'm going to move them to another place. Just imagine that. So that's my initial velocity. The final velocity is in that direction, and I am going to move that until its tail touches the tail of the initial velocity. Wait. Okay, something like that. So that's my final velocity. That's my initial velocity. Okay, and the way to find the change is to take the final velocity minus the initial velocity. And if we do this, we get the answer by joining the tip of the initial velocity to the tip of the final velocity. So that's how we subtract two vectors, right? When you take this vector minus that vector, you get the answer by joining this tip to this tip. So this is the change. This is the change in velocity. Change in velocity, or the difference between those two. Okay. Now, instead of writing out change all the time, I'm going to use a symbol. I'm going to call it delta V. So this curly D here means small change. It's a Greek letter called delta. So this symbol just take it to mean a change in the velocity. Now, in this case, you can imagine just drawing a scale diagram of this, and this will give us the change, the new direction and new magnitude of the velocity. Right. Well, actually, let me just don't use the word delta. Let me just make it simpler. So V, I'm just going to call it, say, W. Alright, I'll just call this magnitude W. And I have this new direction here. Now, in this case, I can describe the new direction quite easily because this angle, since this angle here is pi over 3, we know what's pi over 3. Pi over 3 is just 60 degrees. Now notice one thing about this triangle, that these two sides are equal because it's the same speed here and here. So these two sides are equal, this side and this side. And if this angle is 60 degrees and this is an isosceles triangle, then clearly those two angles are also equal. And I have 60 degrees here and 60 degrees here, and this is actually an equilateral triangle. And what I have now is obviously the three sides must be equal in this triangle. So therefore, if the V there is 3 meters per second, so the length of W must also be 3 meters per second. So I actually have an answer for the magnitude of the change in velocity, and I also have a direction. The direction will be in this direction, and since I know that this angle is also 60 degrees, I know that it is at 60 degrees to the vertical direction. So that actually gives me an answer. But the important point that I want to understand here is how this is related to the force that causes this ball to move from here to here. And as we have seen from Newton's law and the definition of acceleration, the force must be in the same direction as the change in velocity. So if the change in velocity is in this direction, the force must be in this direction as well. Okay, so if you imagine this, think about this direction on the ball during the motion. So we're talking about a force that is acting roughly in that direction. Now, but this conclusion, this understanding of a force acting roughly in this direction, that means same as the change in velocity, is for an average force that acted over this motion between here and here. Okay, at this point we do not actually know if this force is actually different at any particular instant in time. So that's what I'm going to try and find out next.